We want to evaluate the partial derivative numerically using data from the tables for the rate of change of entropy with respect to specific volume holding temperature constant for the fluid ammonia at a temperature of 10 degrees C and that value of specific volume. Well, you can tell right away it's the rate of change of entropy with respect to V holding T constant. So think about S as a function of specific volume and temperature. So the two independent intensive properties are specific volume and temperature. And we want to find not the ordinary derivative, but the partial derivative of S with respect to V holding temperature constant. How would we do that? You would find S minus S, so some change in S, divided by some change in V. Isn't that how we do derivatives? It's the change in S over change in V, or change in F over change in X, something. So this, first figure out the starting point of this derivative. It would be at V sub 1, comma, T. And this V is V sub 1. So what they gave us is right here, that's V sub 1. You're thinking about the specific volume at a particular point. So I'm going to have to get the entropy at that point. That point's defined by the temperature of 10 degrees C and a specific volume of 0.44251. Whatever S is at that point, I need it right here. See that? And then this is V sub 1. Now I need to find another point that's hopefully close to it, but it's going to have to come out of the tables. And so it's going to be the S at a new point. Think about, I'm going to vary V. So I'm going to have to evaluate it at the new V and at the same temperature. So again, I have numeric values for some of these. That's my 10 degrees C. That's my 0.44251 meters cubed per kilogram. This is my 0.44251 meters cubed per kilogram. I don't know what is V sub 2, but it's going to be something in the table. I don't want to. I'm using the table data to approximate this derivative. And then I'm going to want to be able to look up S with that new V2 and the same temperature of 10 degrees C. I don't want to change temperature. All I do is want to change specific volume. So one thing you can do maybe is think about making a brief table, maybe state 1, then state 2. Like this is state S1, S2. It's characterized by pressure. Pressure in units of maybe bar, because that's in our table for ammonia, and temperature in degrees C, and specific volume in meters cubed per kilogram. So go into that table looking at 10 degrees C and 0.44251 and see if you can't find pressure. See if you can't find internal energy, enthalpy, and entropy. Really, it's the entropy is the one we're interested in. These are other properties of interest, but S is the one we really need to focus on. That's kilojoules per kilogram Kelvin, right? So given the it's ammonia, temperature, and specific volume, we find that the pressure is 3 bar, and we find the entropy is 5.6280 kilojoules per kilogram Kelvin. It's on a line in the table, which is nice. Well, where do I find that second state? Again, what do I know about that second state? I know the temperature. True? And I have to find it with a slightly different specific volume. Okay? If you had the appendices in front of you, anybody want to suggest what we do? A lot of times people numerically will do the V2 minus V1 as some value like 0.1, that makes it really hard. But you can do this derivative for something that's not a nice entity like 0.1 or 0.01 for the delta V. Okay? So what do you suggest? Suggest, because they have data in pressure blocks, that I just go to an adjacent pressure block. And I'm already in a pressure block of 3 bar, either go to 3.5 or 2.5 bar. And so if you go to a pressure block of, I think it's 3.5, yeah, 3.5 bar, then I can look up the value of specific volume of 0.37654. So my delta V is not some nice integer number or 0.1 or 0.01 or something like that. It's just this V2 is going to be 0.37654. See that? And then I also look up my S2. My S2 is 5.5417. So what I find is that derivative is 5.5417 minus 5.6280 divided by 0.37654 minus 0.4421. So let's take a look at our units on this. This is kilojoules per kilogram Kelvin. That's the units for the S in the numerator. And then meters cubed per kilogram in the denominator for the change in the specific volume. So kilograms cancel right away. Kilojoule is a kilopascal times a meter cubed. How many people recall that? It's a good one to recall, right? That's very helpful, because the kilojoules go and the meters cubed go. I'm left with a kilopascal per Kelvin. Numerically, this comes out to be 1.3, I'm going to round it off to 1 kilopascal Kelvin. And really, because it's a numerical differentiation, and it's not, the delta V's are not really close together, there's a large error there. So it's approximately that. The rate of change of S with respect to V for ammonia holding T constant. One of Maxwell's relations. Then I find the rate of change of pressure with respect to specific volume holding temperature constant is equal to the rate of change of entropy with respect to specific volume holding temperature constant. These two are switched. Temperature holding specific volume constant. Approximated that derivative numerically, and then we also can interpret, if I needed to calculate dp dt holding V constant at that same point, there's the numeric value for it.